Hi, so this is page 40, 43, and just want to talk briefly about the issue of getting large primes. The recipe for RSA says, the first thing it says is get P and Q prime, and we know we want them to be really big so that it's hard to factor P times Q. And to find the factors, if you're just given n, so we need to have these like ridiculous 100, 200, 300 digit prime numbers, and where could we possibly get that? Because there's no like way we could have a list or anything. So here's the technique we'll use. So Lagrange's little theorem says if Pn is prime, then 2 to the n minus 1 equals 1 in z sub n. The converse says if 2 to the n minus 1 equals 1 in z sub n, then n is prime. And for a long time in human history, people wondered if that was true, and it turns out it's not true. So this converse is not true, but it's almost always true. So we're going to use this as a recipe. So we're going to compute 2 to the p. We're going to compute 2 to some number n minus 1 in z sub n and see if we get 1. We'll use modular exponentiation to do it. And if we do, then we will declare that n is prime and we'll use it for our. It's a pretty safe bet. So it's an incredibly tiny probability that it isn't. The things, if it's not true for things that are called pseudoprimes, okay, so it turns out that if you just start out with any huge integer and start looking at odd numbers above it, like let's take the huge number 15. So we try 15, 2 to the 15th, it turns out won't be, 2 to the 14th won't be 1, it turns out. And so we move on and we try 17, and that works. Yay, it was prime. So in general, you might have to go for quite a while, but not ridiculously long, because there's enough prime numbers out there. Their distribution is thick enough. So embedded exercise 30 really gives a counterexample to this. So if you compute 2 to the 341 minus 1 in z sub 341, what do you get? Well, you'll have to, if you use the program modexp or just do it by hand, you get 1. So that would say, so we hope, or guess, that 341 is prime, but it isn't. So 341 is, I think, the smallest pseudoprime. So the arithmetic, we can do the arithmetic with a calculator of computing this into the 2 to the 340 in z sub 341, without too much work. But back in the day of Euclid or somebody, it was too much arithmetic, and so this conjecture that this converse was actually true probably was exciting for a long time. They thought it might be true, but it turns out it wasn't. So in 2002, these guys, Agrawal, Saxena, and Kayal, found an algorithm, and it's an efficient algorithm, polynomial time, to determine primeness. So if you give it even a huge integer, it can say conclusively and definitely whether or not that integer is prime. And one of the 4050 books, the Neapolitan and some other authors that I've seen, actually does a chapter proving this, but it's fairly hideous and gets into even worse number theory than what we've been doing lately. So we're not going to do it, but you just need to remember that when you compute, when we use this test here to determine that n is prime, there's a tiny, tiny, vanishingly small chance for huge numbers that we're wrong, and that could screw up the whole thing. Oh, and by the way, this algorithm that they came up with, it runs in polynomial time and the number of bits needed to represent it, the candidate number n, but it gives absolutely no clues as to the factors. So if it did give factors, then you could feed the giant integer n into the AKS algorithm, and it would pop out P and Q, but it doesn't. It just says no. So if we form a giant number n by multiplying two giant prime numbers P and Q together and publish it, someone could use this algorithm to determine that it's not a prime number, but they wouldn't give them any clue as to what the factors were. So that concludes this little brief discussion of how we're going to get prime numbers. Except there is code at the website, and I forget what I called it. Let's see I don't want to bother now. I think it's called Find Prime or something. It's pretty obvious. So at the course website, you can find a little application that lasts you for a starting point, and it starts looking at every odd integer after that point to see if, or from that point on, to see if it passes this test. And if it does, it declares it's a prime number and quits. So, and that's what we're going to do right now, is quit. In the next video, we'll prove that RSA actually works.